Atomic Clocks, the race to precision. I'll be your host and commentator, Sam Perrett, and it's quite the spectacle we have in store for you today. Since the dawn of humanity, we've been fascinated with time and the measurement of it, and from humanity's early efforts to measure it with a stick in the sand, we've come a long way. Nowadays, we use a frequency standard. A frequency standard makes use of a stable oscillator. We started with the use of pendulums and advanced to quartz clocks, where quartz being a piezoelectric material, meaning if charges are placed across the crystal, the quartz crystal will bend. The frequency at which this crystal oscillates depends on its shape and size. If an oscillator in the form of electric circuit passes through the quartz resonator, it will eliminate all but one single frequency. The problem with these methods is the manufactural deviations leading to errors between timepiece to timepiece. And while that doesn't matter for telling you if you're late for your 9 AM, cutting edge science needs ever more accurate fundamental constants and a smaller time precision to perform experiments. To explain a better timekeeping method, I'll now hand over to our chief scientist, Barlow.
Thanks, Sam. So as it's been said, precision timekeeping measures from throughout history have been fraught with manufacturing errors. So the natural progression to this was to use atoms as your timekeeping measure, as atoms are all the same and therefore not subject to any manufacturing inaccuracies. So the next question is, how do we actually use atoms as a timekeeping measurement? So the most fundamental concept that allows this is that atoms are found in discrete electronic states. So this means that they have very, very well-defined energies, and that light, in fact, can interact with these states and cause transitions between one perhaps lower ground state up to a higher ground state, or vice versa. So the energy of these states is connected through the Planck-Einstein relation here, where E is our energy of the transition, H is Planck's constant, and nu naught is our frequency. So this frequency allows for a kind of train of pulses in order for us to be able to keep the time. So in order to get the best timekeeping, precision timekeeping method possible, we want to make this Q factor, as it's called, the quality factor, as large as possible. And so this takes in two components. Firstly, the frequency we have from the electronic transition, and secondly, the line width of this frequency, which is shown here. So we want the frequency to be as high as possible, and this really makes sense if you imagine maybe a pendulum that only swings every 1 second, and you'd like to time an event. You may say, oh well, the pendulum, this event occurred when the pendulum swung between swing 3 and swing 4, and therefore you only get a precision measurement being able to say that the event happened between 3 and 4 seconds. Whereas imagine if you had a pendulum that swung perhaps 100 times a second, and then you could say an event occurred between the 334th swing and the 335th swing. So you know the event time is somewhere between 3.34 seconds and 3.35 seconds. So you want to maximize this frequency measure as much as possible. And you also want to lower this line frequency as much as possible, as this essentially tells you how accurately you can measure this frequency here. And that can be done in a number of ways that we'll talk about more when we get into the particular workings of the clock.
Thanks, Kyle. So today we'll be putting forth the most accurate methods to produce atomic clocks against each other in a race to precision through the years. The further along the racetrack they progress, the smaller the fractional uncertainty in the frequency. Introducing our competitors. Firstly, we have Cesium 133, a hot favourite to take the title, using a 2 ground state hyperfine transition from the F=3 to F=4 state, and an impressively high frequency of transition of 9.2 billion Hz. He's looking confident. Secondly, we have Hydrogen 1, looking very swanky in his red bib, using a hyperfine transition from the F=0 to F=1 state. They sport the lowest frequency of transition at 1.4 billion Hz. Next up, we have Strontium 87 sporting a blue number using a transition from the 1s to 3p state, looking confident and with good reason to be, with the largest transition frequency, a massive 429 trillion Hz. Finally, we have Rubidium 87, we're in orange using a hyperfine transition between the F=1 to F=2 state and a frequency of 6.8 billion Hz. And we're ready to go on the start line, and the year is 1950. The crowd are going wild in anticipation.
Woo!
3, 2, 1, and we're off! Go, go, go! And it's a slow start by everyone in 1950, moving into 1951. 1952, development has started on the Cesium clock by the National Physical Laboratory in the UK. The apparatus used for this measurement is named NBS-1. In 1953, development is continuing on Cesium, but yet to break away from the pack. Over to Kyle to find out what they're actually trying to measure.
The clock transition for cesium is the energy splitting between the first two hyperfine levels of the cesium atom. Firstly, what are hyperfine levels? Well, they arise from the interaction between the nuclear spin and the electron spin. So what you can get is two different energy levels depending on whether or not the nuclear spin and the electron spin are aligned, which gives a higher energy, or whether the nuclear spin and electron spin are anti-aligned, which gives a lower energy. And in cesium, this change between the total spin of both the nuclei and the electron, F equals 4, and the total spin of the nuclei and electrons, F equals 3 here, is around 9 billion hertz.
1955, and Cesium storms into the lead with a fractional acidity of 1 × 10⁻11. The National Physical Laboratory in England builds the first Cesium beam clock used as a calibration source. So back to our in-house scientist Kyle to explain how the Cesium clock works.
So, how does the Cesium beam clock work? Firstly, Cesium atoms are heated up within a chamber and then ejected through a small hole in this chamber into a thin beam of Cesium. This beam of Cesium is made up of roughly equal populations of the two hyperfine ground states. So this beam then goes through a state deflecting magnet that causes the atoms in the F equals 4 state to be absorbed by some wall, and then the only atoms entering the microwave cavity will be the F equals 3 atoms. So the microwave cavity is made up of two regions. The first region applies a 90-degree pulse on the atoms around their resonant frequency, and this causes a coherent superposition between the two hyperfine ground states to form. Then after some time in this region here, the atoms then go through the second part of the interaction zone, which applies another 90-degree pulse, causing all the atoms to flip into their excited state. Well, at least if it was perfectly on resonance. So then, after this, all the atoms exit the interaction zone and then go through another state deflecting magnet. However, this time the state deflecting magnet chooses to dispose of the F equals 3 atoms in the state, and therefore keep the F equals 4 atoms within the beam to a detector. Now, we know that this system is in resonance when we get the maximum amount of F equals 4 atoms going through the system. As we start with F equals 3, if we have perfect resonance within the microwave cavity, every single one of these cesium atoms will be in the F equals 4 state. So in order to calculate this, the detector sends a signal to some electronics down here, and then to a quartz oscillator. And what this quartz oscillator will do is slightly change the frequency it uses in the microwave cavity in order to find the exact point of resonance within the system. So now let's look more closely at the microwave cavity. This microwave cavity is made up of two different interaction zones, here, and it is known as the separated oscillatory field method. So what this method allows is for very long excited states of molecules, for this superposition here to last as long as possible. Now, the impact of this is shown by Heisenberg's uncertainty principle. So if we have a large excited state, as in we have a large uncertainty in the time of the excited state, therefore we have a lower uncertainty within the energy of the transition. And as we've seen, the energy of the transition is connected to the frequency. And so therefore it can be shown that for longer interaction times in this cavity, this leads to a smaller line width. So the line width is inversely proportional to the interaction time t. Here.
1956 into 1957, no major developments occur and Cesium is still sitting pretty out in the lead. So Kyle, why was Cesium chosen to be the first atomic clock?
Well, a brilliant question, Sam. So firstly, cesium is a very simple atom as it only has a single s electron in its outermost shell, making it a hydrogen-like atom and therefore a very simple system to study. Secondly, it is the most heavy atom in the alkali metals, and therefore this causes the cesium to move the slowest and therefore leads to the largest interaction times and the smallest line width. Thirdly, and perhaps a more subtle point, is to do with Zeeman splitting, which is the splitting between levels due to the presence of an external magnetic field. And if we have integer total spins of the nuclear and electron spin, then in a first order Perrett bit of calculation, these levels at MF equals 0 in fact do not change with the application of a magnetic field. And quite often, in fact, in some atomic clocks, there's a small magnetic field applied that produces this splitting in order so they can exactly pick out this MF equals 0 level and stop stray magnetic fields from perturbating your system.
1958, and Rubidium has liftoff with Bender, Beatty and Chi producing a clock with a relatively large uncertainty of 3 × 10⁻⁹. Let's go back to Kyle to get the lowdown on how it works.
The rubidium atomic clock works different than the cesium atomic clock as it doesn't use a beam of atoms but rather a gas of atoms. So firstly, a rubidium discharge lamp is used to create light corresponding to the frequency from this P level to the excited state hyperfine level, and also from this P level to this ground state hyperfine level. This then goes through a rubidium buffer gas. Now this is a different isotope of rubidium. This is rubidium 85, and the discharge lamp in resonance cell uses rubidium 87. But by a complete coincidence of nature, this rubidium 85 has a transition that exactly maps onto the transition between the P state here and the F equals 2 singlet state here. So this absorbs all of this light from this transition and leaves a pure light from this P state to this ground hyperfine level. Then this light here travels into the resonance cell. Now what this does is it excites many of the atoms in this cell and promotes them to this P state up here. These then decay almost half into the F equals 2 state and a half into the F equals 1 state. But as they decay into the F equals 1 state, another photon of light will come along with this frequency and then excite it again. And therefore, as time goes on, you get a population inversion where the first excited hyperfine level of the rubidium atom is more populated. So what you do now is apply a microwave frequency corresponding to this energy splitting into 2 hyperfine levels, and therefore you can start stimulated emission from these hyperfine levels, and therefore bring the population of the states back down to this F1 level. So if you're exactly on resonance with this hyperfine level here coming from the microwaves, then you will populate this F equals 1 state again, and the intensity of light coming from your discharge lamp will decrease. So in order to obtain the resonance signal you want, you're looking for this detector to detect the least amount of light coming from this rubidium discharge lamp.
1959, and a further boost to cesium as MBS2 goes into operation with a fractional uncertainty of 8 × 10⁻12. They achieved this by reducing the line width and increasing the Ramsey cavity, and hence having longer interaction times, as Kyle explained. 1960, and the first hydrogen maser is produced by Norman Ramsey and storms ahead of rubidium and up to 2 × 10⁻11. A great start. Let's go back to Kyle and he'll tell us how Ramsey produced the first hydrogen maser.
This is a diagram of a hydrogen maser. So firstly, we create a beam of molecular hydrogen using a tank of H2 molecules. This beam is then put through a discharge arc where the molecular hydrogen will dissociate into hydrogen atoms. Then after this, we'll have a hydrogen atom beam that goes through a state deflecting magnet and gets rid of the ground state hyperfine levels and only keeps the excited hyperfine levels. This then goes into a microwave cavity with a storage bulb inside. So the atoms will decay and also reabsorb emission from the other atoms in the bulb, and therefore will resonate at the frequency of this hyperfine transition. Just a little side note, often an external magnetic field is applied to this in order to break the degeneracy of the Zeeman sublevels. This causes a more sharper line width, and also the entire cavity is surrounded by mu metal, which eliminates any external magnetic fields, and therefore we have no perturbation within the system.
1963, and the search for a clock with improved accuracy and stability results in MBS3. A further decrease in uncertainty to 5 times 10 to the negative 13 sees cesium storm ahead even further. The length of the Ramsey cavity was more than twice as long as the previous MBS2, which was considered phenomenal for the era. Another 2 years passed, and 1965 MBS4 was unveiled, a further boost to cesium. While being much smaller than its predecessor, it operates at much longer times, and so has a higher stability. This had an uncertainty of 3 times 10 to the negative 13. Into 1966, and MBS5 is developed, pushing cesium further forward to 1.8 times 10 to the negative 13. This was a huge machine with a Ramsey cavity of 374 centimeters. 1967, cesium makes a bit of history as the second is redefined as the duration of 9,192,631,770 periods of the radiation corresponding to the transition between the two hyperfine levels of the ground state of the cesium-133 atom. In 1974, there were significant modifications to MBS5. The improvement was a direct result of more effective filtering of the high-velocity atoms and a reduced velocity of the atomic beam. This was renamed the MBS6 and had an uncertainty of 8 times 10 to the negative 4, cesium pushing further ahead. The development of rubidium and miniaturization means it's now cost-effective to be used in applications in space. In 1974, the Timation 3 satellite was launched containing a rubidium clock with an uncertainty of 10.4 times 10 to the 11. A small step forward. 1981, we have a significant breakthrough in hydrogen maser technology. The so-called active maser achieves an uncertainty of 2.6 times 10 to the negative 15. Hydrogen storms into the lead. 1987, hydrogen further extends its lead by cryogenically cooling the maser to limit white noise from thermal fluctuations of the cavity. This sub 1 Kelvin temperature allows a reduction of uncertainty to 1 times 10 to the negative 15. 1988, and cesium claws back some ground with the new National Institute for Standards and Technology developing NIST-7. This achieves an uncertainty of 5 times 10 to the negative 15. It used the newly available narrow line width lasers for state selection and detection, thus replacing the magnets and detectors found in earlier standards. 1999, and further development by cesium as the NIST-F1, the first cesium fountain clock with an uncertainty of 1.7 times 10 to the negative 15. Over to Carl to see how the new technology works.
Improvements to the cesium beam clock eventually led to this, the cesium fountain clock. So this works on essentially the same principles as cesium beam clock, however it makes use of gravity in order to decrease the amount of interaction zones from 2 to just 1 microwave cavity. So this only became possible with the invention of lasers and laser cooling. So essentially 6 perpendicular lasers are used to coalesce cesium atoms into a ball. This ball is then held in place until these vertical lasers are detuned, and then this causes the ball to fly up through this microwave cavity. So as it travels up through the microwave cavity, we get the same superposition of states in the excited and ground state hyperfine levels. And then as the cesium ball slows down due to gravity, it then starts to move downwards again through the microwave cavity once again, causing excited state cesium atoms to be produced. These then travel through a probe laser, and this probe laser causes stimulated emission from the excited to the ground state hyperfine levels. So therefore, in here where the atoms are supercooled in almost all in the ground state hyperfine level, when we come up here, go through the microwave cavity once, back down, go through it again, we want to end up with the most excited state atoms. And the way to measure that is if the probe laser measures the highest intensity of cesium excited state atoms. And therefore, if this detects the strongest signal here, we know that this microwave cavity has been tuned to the resonance of the cesium atoms. So the biggest difference with this system here is that we get far longer interaction times due to the use of gravity. As these cesium atoms move up about 4 meters per second, and we can actually get up to about a second of interaction times within this system, narrowing the line width a lot.
2005 Rubidium makes some improvements, but it's still lagging behind. It peaks out at 1 × 10 to the negative 13. Collisions between atoms in a resonance chamber limit the interaction time and therefore give a wider line width. It seems a buffer gas just cannot get the lowest uncertainty. But it will hold a place in our hearts as the industrial workhorse providing our GPS. It looks destined to finish last. 2008, and out of nowhere, Strontium finally makes an appearance, steamrolling into the front of the race. Advancements in technology finally allow scientists to measure optical frequencies, as previously only microwave and radio waves were detectable to a high degree of accuracy. Over to Kyle to explain a strontium clock.
Now we'll look at a strontium atomic clock. Now, strontium atomic clocks are known as strontium optical lattice clocks. So, the optical bit comes from the clock transition we measure is in an optical regime. Therefore, we have a higher frequency and a higher quality factor to go along with that clock. Secondly, it is known as a lattice clock because of these 6 lasers perpendicular to each other cause a potential energy landscape in the centre of these lasers that can cause individual atoms to be localised to a single spot in a large lattice. So what this large lattice allows is for the scientists to control the interactions and collisions between the strontium atoms and in fact completely eradicate collisions and minimise interactions almost entirely. So the fact that there's no collisions or interactions allows these strontium atoms to have very long lifetimes and therefore very long interaction times, and this allows for us to have a very narrow line width and therefore again a higher quality factor of the clock. So this works differently from other clocks as we do not try and tune some external frequency to the resonance point. All we do is use a probe laser in order to kind of pump the system up into excited states and then measure the fluorescence that comes from the strontium atoms. And this fluorescence is in the optical range and therefore must be measured using frequency combs. Frequency combs are a kind of ruler that allows you to very accurately measure optical frequencies. So again, this has only come about recently due to the invention of frequency combs and optical lattices. And this clock has an incredibly high quality factor and therefore an incredibly low fractional uncertainty.
Can anyone catch strontium? Time is running out. 2014 and Cesium makes a late surge with the new NISTF2, a second generation of fountain clock, utilising cryogenic cooling to further reduce the uncertainty to 1.5 × 10 to the negative 16. A valiant effort, but not enough to catch strontium. And up to present day, and refining of the new optical cones and laser cooling, the strontium rubs salt into the wounds and breaks 10 to the negative 17, with a record low of 6.4 × 10 to the negative 18, a clear victor. And that concludes the race to the present day. Let's give you a rundown of the final results. In last place for industrial workhorse and most commercially available, Rubidium 87 with a final uncertainty of 1 × 10 to the negative 13. Onto the podium in third place, falling behind after the mid-race lead, Hydrogen 1 with 5 × 10 to the negative 16. In second place, the original OG atomic clock, Cesium 133 with 1.5 × 10 to the negative 16. And our victor, currently the most accurately frequency standard, the new kid on the block and storm into a late victory, Strontium 87 with an unbelievably low certainty of 2.6 × 10 to the negative 18. A round of applause for our 3 victors and our overall winner, Strontium 87, who takes home the trophy and medal. So that concludes our race. I hope you enjoyed it and learned something new about atomic clocks. Goodbye from our chief scientist, Barlow.
Goodbye.
And goodbye for me. Goodbye.